Hello, welcome to my lecture presentation on Chapter 4, Subtopic 4.4, Intermolecular Forces. First and foremost, let's look at the topic overview. When we talk about intermolecular forces, our main focus is on simple covalent molecules because intermolecular forces are found between this type of molecules. In the first part of this topic, I will illustrate the difference between inter and intramolecular forces. Next, I will introduce the types of intermolecular forces, followed by explanation on how the forces arise. Then we'll move on to factors affecting the strength of each force. And lastly, the effect of intermolecular forces on physical properties of compounds. Introduction. I have two diagrams in this slide. The first diagram has one HCl molecule. In the second diagram, there are several HCl molecules shown. The line interconnecting the hydrogen and the chlorine atoms in the first diagram is the covalent bond between the atoms, or so-called the intramolecular force. In the second diagram, there are several red broken lines, and these lines are interconnecting the HCl molecules. Those red lines are attractive forces between the HCl molecules. So by taking a close inspection on these two diagrams, are you able to see the difference between intra and intermolecular forces? Simple, right? Well, by definition, intramolecular forces are forces that hold atoms together in a molecule, while intermolecular forces are those attractive forces that exist between molecules. In this slide, I will be comparing the energies needed to overcome the inter and intramolecular forces. I have here two H2O molecules shown. H2O molecule is polar. The partial plus and partial negative are clearly labeled on each atom in the molecules. In one H2O molecule, there are two covalent bonds, two OH covalent bonds, which are intramolecular forces. Now, this line in red, broken line in red, that has just appeared, indicates the intermolecular hydrogen bond. Well, how much energy do you think is required to break this hydrogen bond? It is 41 kilojoule per mole, whereas 930 kilojoule per mole of energy is needed to overcome the intramolecular covalent bond. Comparing these two values of energies, we can easily conclude that intermolecular hydrogen bond is weaker than intramolecular covalent bond, since the energy required is so much lower. Generally speaking, intermolecular forces are much weaker than covalent bonds in a molecule, and they are also responsible for the distinctive physical properties of a covalent compound, such as the physical states, the melting and boiling points, the solubility, and many more. Let's move on to the types of intermolecular forces. Basically, there are two types of intermolecular forces. The first, van der Waals forces and the second hydrogen bonding. There are two breakdowns of van der Waals forces. The first is the dipole-dipole forces or permanent dipole forces. And in our syllabus, it is written as dipole-dipole interaction. Any one of these terms can be used as they are all similar. The second type of van der Waals forces is the London forces, also called dispersion forces. Hydrogen bond is a type of dipole-dipole interaction because it exists between polar molecules. Hydrogen bonding is conditional, meaning that the molecule must contain FH, OH, or NH bond in order to exhibit hydrogen bonding. Now, let's look at the relative strength of intermolecular forces. I have listed down the three forces. Between these three forces, hydrogen bonding is the strongest. And between the two van der Waals forces, the dipole-dipole forces is stronger than the London forces. In this slide, I will be elaborating on dipole-dipole forces. Dipole-dipole forces exist only between polar molecules. Back to your pre-knowledge on molecular polarity. I guess by now, you should be able to predict whether a given molecule is a polar or a non-polar molecule. In a polar molecule, the partial positive end of one molecule will attract the partial negative end of another neighboring molecule, as shown in the diagram. I have two diagrams here. Solid and liquid molecules of the same compound. Since all the molecules are polar, which means that they have permanent dipole, the attraction between one molecule and another, the so-called dipole-dipole forces, are very strong. Well, the polar molecules must be in close proximity for the dipole-dipole interactions to be prevalent. Close proximity here means that the molecules must be very close to each other. They even touch each other in order to be attracted to one another. But in drawing, in our diagram, we would normally just use broken lines to denote the dipole-dipole forces. So I have two polar molecules in this diagram, and the attractive forces between them is the dipole-dipole force. Since different polar molecules have different level of polarity, dipole-dipole forces increase with the increase in the polarity of the molecule. The more polar the molecule, the stronger the dipole-dipole interaction. Well, this is another diagram showing example of dipole-dipole interaction between HCl molecules. Yeah, HCl is a polar molecule. London forces. This is the second type of van der Waals forces. In this slide and the next three slides, I will be elaborating on London forces. Dipole attractions also exist between non-polar molecules such as chlorine, nitrogen, carbon dioxide, oxygen, and noble gases such as neon, argon, and etc. The dipole attractions between the nonpolar molecules are known as London forces or dispersion forces. Since the molecules are nonpolar, then how do London forces arise? So this will be explained in the next slide. London forces arise due to the random movement of electrons in an atom or in a molecule. So this is a nonpolar molecule. You can see that the electrons are distributed within the molecule and they are actually moving. Moving randomly. When these electrons revolve around the nucleus, at any given instant, the electron cloud density might be higher at one end than the other. So this will give rise to a temporary dipole, as depicted in this diagram. So the electrons are revolving around the nucleus. At a certain instant of time, it may so happen that the electrons accumulate on one end of the molecule, leaving the other end having fewer number of electrons. So this will give rise to a temporary dipole. So the molecule looks like distorted. There's one end with high electron density and the other end low electron density. So the molecule becomes polar, temporarily polar. So there is a partial minus n and a partial plus n. So this molecule is said to have temporary dipole or instantaneous dipole. So from a nonpolar molecule, due to the random motion of electrons, giving rise to a temporary dipole. Due to electron repulsion, a temporary dipole on one molecule may induce a similar dipole in a neighboring molecule. In this diagram, you can see how a nonpolar molecule transforms into a temporary dipole molecule due to the random movement of electrons, which has just been discussed in the previous slide. Once a temporary dipole molecule forms, when another nonpolar molecule comes nearby to this molecule or comes near to this molecule, this temporary dipole molecule will induce similar dipole in the nearby molecule. So the nearby molecule now becomes an induced dipole molecule. Well, how does this happen? This is because of electron repulsion. When this molecule previously was nearby this temporary dipole molecule, since this end of the temporary dipole molecule is lacking or deficient in electron, the electrons in this nearby molecule will all rush to this end. So a dipole forms. This end of the molecule becomes electron rich, while this end becomes electron deficient. So a dipole is induced. So bear in mind that these two molecules are very close to each other. Since both molecules now are having a dipole, these opposite charges between these two molecules will attract one another. So this is the force of attraction indicated by these broken lines here. So this force of attraction between this temporary dipole molecule and the nearby induced dipole molecule is known as the dispersion force or London force. So you may go through the text here. I'll give you some time to re-observe the diagram and to read along with the text. So is that clear to you? How London forces arise? Okay? All right. London or dispersion forces become stronger with the increase in the number of electrons in atoms and the molecular size. Bigger molecules, more polarizable. And we have a note here. London forces also exist between polar molecules. Yeah, earlier on, when we elaborate on London forces, we focus more on non-polar molecules. But bear in mind that London forces also exist between polar molecules. Polar molecules have both dipole-dipole forces and London forces. The term polarizability refers to the ease of distortion of electron clouds of atoms or molecules. Yeah, in the next slide, I will show you diagram to make you understand the meaning of polarizability. Why bigger molecules more easily polarize? Well, as you can see, I have two diagrams here to help illustrate the term polarizability. I have one big molecule and another a small molecule. As you have learned, in periodic table, that when the size of a molecule is big, or the size of the atom is big, the distance between the nucleus and the electrons are further apart. So that causes the electrons to be held more weakly by the nucleus compared to a small atom where the distance between the nucleus and electrons are closer. So the electrons are more tightly held or strongly held by the nucleus. So in a big molecule, the electrons are more freely to move about randomly. So during the electron movement, since the electrons are loosely held by the nucleus, so it can easily get distorted and forms a dipole. compared to a small molecule where the electrons are more strongly held by nucleus. So during the random motion of the electrons, it will not that easily get distorted. So big molecule is more easily polarized, while small molecule hardly polarized. So that is why when the molecule is big, the London forces is stronger, because it can more easily form a dipole. Or from a non-polar, it easily turns polar temporarily. So that's the meaning of polarizability. Yeah, I hope you can understand better with these two illustrations.